A huge thanks to Brian for sponsoring this video. A really fun one from the AIME 1989. We have to find n, element of natural numbers, which satisfies 133 to the fifth power plus 110 to the fifth power plus 84 to the fifth power plus 27 to the fifth power is equal to n to the fifth power. And this right here is a lot of fun, a little bit of try and error, a little bit of very clever bounding, but it gets the job done and it's a splendid exercise, so definitely make sure to try it out for yourself. And once you're done, keep watching the video for solution. By the way, don't forget to check out me playing with my wood over on Flammy's Wood, links down there in the description. And now we are going to dive right in. So as mentioned in the introduction, we want to bound this one right here. Back in the days, there were no calculators allowed, like 1989. You had to do stuff like this on your own, with your hands and just your brain. So let us bound n in some kind of way, such that we don't have to calculate too much stuff. Now, one thing I would like to mention at first, how we want to bound it, is by binding it in some kind of way with fifth powers, because all those odd powers are strictly increasing. Like to the third power looks like this, okay, in the positives it's strictly increasing and the like. Same for the fifth power. Meaning if we were to find some kind of upper and lower bound, for example n being bounded by a to the fifth power and also b to the fifth power, then by the monotonicity, that's a weird word, of the fifth power we can take the fifth root on both sides, meaning we can just bind n between b and a. And we want to find such b and a's. Now the first bound is actually rather easy to find, because if we just take a look at those three numbers, 110 to the fifth power plus 84 to the fifth power plus 27 to the fifth power, we are going to notice that since those are all positive numbers, and if we raise it to some kind of exponent they still are positive, then we have that, well, 135 to the fifth power plus this positive thing is always going to be strictly greater than 135 to the fifth power. But since all of this is equal to n to the fifth power, we have our first bound that n to the fifth power is always greater than 135 to the fifth power. This is our first bound. Now we have bounded it from below, let's bound it from above. And there are actually several ways to do so, but we want to make our life easier. What we want to do is, it really doesn't matter which number you want to pick, but we want to find basically an upper bound to all of these numbers as being a multiple of one of those bases in some kind of way. This way we can factor out the common base to the fifth power, and then we can still bound the other factor that we get by some kind of fifth power. Now, to make our lives easier, we are going to choose the smallest number. For the lower bound, we have chosen the biggest number to the fifth power, and for the upper bound, we are going to choose the smallest number. And now we are going to take a look at all the multiples, which are basically greater than those bases that we got right here, multiples of 27. Now, 27 to the fifth power is already some kind of factor of 27. To the fifth power. Now what about 133? Now what are the multiples of 27? 27, then we get 54. After that we are going to get 54 times 3. 27 times 3, I'm terribly sorry, is going to give us 81 in the process, meaning 81 is still below 84. One more, it's going to give us 108. So our 84 to the fifth power is most definitely smaller than 108 to the fifth power, and 108 was 27 times 4, so this is 27 times 4, and all of this to the fifth power. Now what about the next ones? 110 is still bigger, so the next power, or the next multiple of 27 is going to be 135. That's my most favorite number, by the way. And 135 actually bounds 110 and also 133 from above. So 133 to the fifth power is less than 135 to the fifth power, which is the same as 27 times 5 to the fifth power. And same thing here, we have 110, okay, to the fifth power is the same bound. So now we have bounded basically our n to the fifth power from above, meaning consequently, if we just get everything together, we have that n to the fifth power is less than all of those multiples of 27 to the fifth power added together. So we are going to get 2 times 135 to the 5th power, which is the same as 27 times 5 to the 5th power. We can distribute the 5th power into here. So 2 times 27 to the 5th power times 5 to the 5th power. And then we are still going to have 27 to the 5th power. So plus 27 to the 5th power plus, and then we are going to have 27 to the 5th power times 4 to the 5th power. Meaning if we were to factor out our 27 to the 5th power, we are still going to have the other factor of 2 times 5 to the 5th power. Okay, 5 to the 5th power. Let's see, so 2 times 5 times 5 is 25, then 125, 625, 3125 plus. Then here if we factor out the 27 to the 5th power, we are going to get 1. That was easy. Plus, and now we are going to get 4 to the 5th power. This is the same as 2 squared to the 5th power, which is 2 to the 10th power. This is 1024, not much to think about here. Meaning our upper bound at the moment is 27 to the 5th power. Now 2 times 3125 is going to give us overall 6,250, and 1 plus 1024 is going to give us 1025. So if we were to add those two together, we are going to get times 7,275. Now this right here is a proper upper bound, but the thing is, as mentioned at the start, we want to bound it by some kind of a to the 5th power from above. Now we already have 27 to the 5th power. 7,275, as a matter of fact, is not something to the 5th power. But we know something which was really close. 5 to the 5th power was 3,125. Why not try it out with 6? So what is 6 to the 5th power? Maybe we can bound this 7,275 from above once again by 6 to the 5th power. Now 6 to the 5th power is 6 times 6, which is 36, times 36 times 6. 36 times 6 is the same as 180 plus 36, which is going to be 200, so plus 200, plus, 36, 216, if I'm not mistaken. Yes, 216, and if we were to add those together, we are going, multiply those together, we are going to get, okay, 216 times 3, basically, or times 30 is going to give us 648, so 6,480 plus, and now 6 is the double of 3, meaning just 648 doubled, which is 1,296 exactly, meaning we are going to get overall 7,000. That's a lot of calculations, so we are going to get a 6, a 7, then we are going to get a 7 here, 7,776, which is most definitely above our, so this right here is less than 7,776, which is the same as 6 to the 5th power. Meaning n to the 5th power consequently is once again less than 27 to the 5th power times 6 to the 5th power, which is the same as 27 times 6 to the 5th power, which is equal to 27 times 6, this is 120, 162 to the 5th power. Meaning we have successfully now bounded our n. Meaning, consequently, n to the 5th power is less than 162 to the 5th power, and it's also greater than 133 to the 5th power. There was a lot of mental calculation, but it's going to work out nicely at the very end. There was a lot of work initially, but it's going to make our life easier. Because strictly increasing 5th power, we can use the 5th root on both sides, giving us 133 is less than n, which is less than 162. So we now have a total of 28 numbers that we could check. But how in the world should we plug all of those numbers into here and then check to the 5th power? This is just not humanly possible in the time restraint. What we are going to do here is we are going to make use of remainders, basically. And as a matter of fact, before we get started, I want to introduce something which just gets the idea of modular basically across. Modular arithmetic, that's very thick, basically. Basically just working with remainders. I'm going to give you a few examples. So the first thing I want to mention is if k divides some number p, this just means dividing it without a remainder, then that also means that k also divides p to the nth power. This is easy to see. You can generalize this, you can prove it. It's very easy to see, but just let me give you an example. Obviously, 2 divides 6, because 6 is the same as 2 times 3. But if we now raise 6 to the nth power, then 6 to the nth power is the same as 2 to the nth power times 3 to the nth power. Okay? And this also means that 2 divides 2 to the nth power times 3 to the nth power, which is the same as 6 to the nth power. I think you can see this, okay? This does make sense. So if a number divides another number, then this number obviously also divides the power. And the same thing holds for modular arithmetic if we calculate modulo. Meaning if we basically have the addition of powers right here, and we want to take a look at the remainders modulo 2, for example. Then what that means is we can also just take a look at the remainder where all of those 2's, for example, cancel out. If we take a look at modulo 2, then we can just get rid of all the 2 to the 5th powers, for example, all the 2's that aren't there, and we are going to be left with, for example, all the other numbers to the 5th power. This is just what modular arithmetic means, and we're going to take a look at another example. So just for modulo, if you're not familiar with that, if we take a look at 7 mod 2. Then we are going to see how often does the 2 fit into the 7, obviously 3 times, but there's still 1 left, meaning 7 modulo 2 is the same as 1, basically, because we have a remainder of 1. And we're going to check a bunch of numbers such that we can take a look at our bounds that we got right here, and we're going to reduce the number of numbers which are still left in the pool, basically, and then we can bound it even more using modular arithmetic. It's just playing around with remainders in this idea up here that we can divide through a bunch of numbers, check once again, up until we get rid of, for example, all the 2's in there. Okay, let us take a look at the number 2 first. N to the 5th power is congruent 2. Now, if we were to take a look at all of those modulo 2, then just go through the idea once again. With the to the 5th power, instead of checking our 5th power, we are going to check the individual number. 133. What is next to 133, which is divisible by 2? Obviously 132, meaning we have a remainder of 1, meaning 133 to the 5th power modulo 2 is the same as 1 to the 5th power. Plus. Now what about 110? 110 is divisible by 2, so 110 to the 5th power is also divisible by 2, meaning we are going to get a remainder of 0. Plus. Now 84, same idea, 0. Plus. And for 27, we have 26 as being our number below it, meaning we have a remainder of 1 once again. 1 to the 5th power, and all of this modulo 2. Now 1 to the 5th power is 1, 1 plus 1 is going to give us 2, meaning 2 mod 2 is just think back to here, 0. So n to the 5th power is consequently equal to 0 mod 2. What this also means is that n to the 5th power doesn't have a remainder if we divide it by 2. Meaning it's an even number consequently. So n is definitely an even number. So we can already reduce the amount of numbers that we have right here in the pool. Namely what we have is that 134 is a number that works, so 136, 138, up until 162 basically. But we can choose 162, it's strictly less than 162. So yeah, let us restrict it a bit more. What about 3? So using divisibility rules here, regular ones with the with the digit sum and the like doesn't work out nicely with the fifth power. So we have to go through the same procedure once again to make our life easier. Now, what's about 133? 133, what is next to it? So 120 is divisible, so we got 13 left. Then 12, we got 1 left. So we got a remainder of 1 once again. 1 to the fifth power. What about 110. 110, so 90, then we have 20 left. There, it fits 6 times into there. 18, we get a remainder of 2. Plus 2 to the fifth power. Plus, so 84. 84, so 90 is above it. Minus 6, which is divisible by 3, gives us 0 modulo 3. Plus, and now we got 27. Obviously, this is 3 cubed, meaning we get 0 modulo 3. All right, meaning n to the fifth power is congruent to, so this is 1, 2 to the fifth power is, this is 4, this is 8, this is 16, 32. So we are going to get 33 modulo 3. And, well, 33 is most definitely divisible by 3, meaning we are going to get a remainder of 0 modulo 3. And consequently, once again, n to the fifth power is divisible by 3, and it's also divisible by 2. If it's divisible by 2 and 3, we also know that it's going to be divisible by 6. This restricts it very nicely. So n is bounded, so just a little reminder, n is bounded between 133 and 162. And it can only be multiples of 6 now, since we know this from the modular arithmetic part. Meaning, what is close? 120, then 132 doesn't work. Meaning n can be equal to 138 or to 144, or it can be equal to 150 or 156. Those are the only 4 numbers left. Let us go a bit further. What about the number 4? N to the fifth power, congruent to 133. 133, so 120 is next to it, 12 is divisible by 4, so we are going to get a remainder of 1 plus, let us speed run through it, 110. 110, 120 is next to it, no, that is too much. 12 less, 108, meaning we get a remainder of 2 to the fifth power. Plus, so what about 84? 84, 80 is divisible by 4, then we get 4, meaning it's 0. Plus, and now 27. 27, 28 is above it, 24 is less than it, meaning we're going to get a remainder of 3 to the fifth power, and all of this modulo 4. Okay, now this is going to be just 1. 1 plus, we know that 2 to the fifth power is the same as 32, so we are going to get 33 plus 3 to the fifth power. Okay, 3 times 3 is 9, 27, 81, and after 81 comes 243. Modulo 4, or in other words, this is congruent to 276 modulo 4. Now 276, 280 is divisible by 4, meaning 4 less than 280 is 276. It's congruent to 0 modulo 4. Okay, good job. Meaning it's also divisible by 4. Let us check those numbers. 138, 120, no, it's not divisible. 140 would be divisible by 4, so this right here can fuck off. Now 144 is obviously divisible, then 4 more, no, 150 doesn't work out, but 156 indeed does. Okay, we got 2 numbers left. Now, what about congruent modulo 5? So 5, n to the fifth power is congruent to. So 133, let us just check. No, 135 is more than less, so 3 to the fifth power plus 110. Obviously, it has a 0 at the very end, and meaning it's going to be congruent to 0 modulo 5. Now, 84 now. 85 is too much, so less. We are going to get 4 to the fifth power as a remainder, and then 27, 30 is more, so we're going to get a remainder of 2 to the fifth power, and all of this modulo 5. Now 3 to the fifth power, we already know this is 243. Then we are going to get 4 to the fifth power is 2 squared to the fifth power, which is 2 to the 10th power, 1024. Plus 2 to the fifth power is 32 once again, and all of this modulo 5. Okay, and well, 243 plus 32 is going to give us 275. 275, and if we add this to 1024, we are going to get that this is congruent to, let me see for a second, so 1200, what did I say, 200, I'm terribly sorry, 75, so 99, right? Modulo 5. Hope I didn't mentally fuck up, but this should be correct. Now, what does it mean for something to be blah 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 modulo 5? We can either say that we are going to get 4, obviously, since 1300 is above. This is 4 mod 5. Or we can also say that this is -1 mod 5. But let me just bring my point across, because this right here is going to be important. We are going to have a remainder of 4 in some kind of way, modulo 5. Meaning, remainder of 4 means it's 1 less than a multiple of 5. Just think about that. If we have, for example, let's say 29 mod 5. Then, okay, 5 fits 5 times into there. We are going to get that this is 4 mod 5. Once again. So this is 1 less than a multiple of 5. Or we can just go through the calculations here. 144 is most definitely mod 5, 4 mod 5 obviously. But 156 is 1 mod 5, because 155 we have 1 more. So this right here is out of the game, meaning our solution is that n must be equal to, it must be equal to, with a big fat exclamation mark, 144 or 12 squared. So we actually get that this is 12 to the 10th power in the original equation, which is pretty cool if you ask me. And yeah, that was a very fun question. I really did enjoy it. And if you do enjoy problems like these, number theory, Euclid's algorithm, for example, modular arithmetic, then Brilliant might be the perfect fit for you. Woo, boys, I tell ya, it's getting hot in here, and it's not because of Papa Euleroyd or because all the windows are closed and it's 30 degrees Celsius out there. No, most definitely not. It's getting hot in here because of today's sponsor, Brilliant. They do not only have mathematics, physics, computer sciences, whatever you're striving for to learn in the STEM field over on their website. No, they also back all of their courses up with their amazing interactive learning concept, which is a one of a kind on the internet. I for myself am an avid Brilliant user myself, and I use it on a weekly basis to either teach stuff to my class or maybe just to brush up on old topics which I have already forgotten, or to just refresh a tiny little bit of knowledge. Brilliant is seriously unique, and all of their courses are backed up, as mentioned before, by interactive content. Chinese remainder theorem, just remainders in general, can be visualized nicely using blocks or the like. Apples, for example, analytic apple theory. And yeah, this is what they bring across using visuals. You can play around with blocks and the like, or maybe in the calculus section play around with graphics. In the geometry section play around with triangles. You can play around with so many things over there, it's ridiculous. And you can experience the mathematics, physics, etc. on your own, using your own two hands, just trying around a tiny little bit, varying parameters, stacking up stuff, taking a statistic, and just varying things in there. There's so much to explore. And the time in my sponsored message is not even close to enough to fully explain what Brilliant is capable of in terms of transferring knowledge to their users. And the best way to experience Brilliant is just to experience it by yourself, just trying it out for free, at least a big portion of it, by using the link at the top of the description, brilliant.org/FlammableMaths. But even better than that, the first 200 people to actually make use of the link also get 20% of an annual premium subscription, and also full access to the whole repertoire that Brilliant has in stock for you. It's an awesome deal, seriously. They have so much content available on their website. You won't get it done in a year, even if you work daily on Brilliant. So much stuff going on over there, and they're adding new courses on a regular basis, so much more content coming. I just can't emphasize how much I love Brilliant. They got a great team backing them up. They got experts in their field creating the courses for them, and it's just wonderful. It's a wonderful experience and you should most definitely try it out. So yeah, try it out and support the channel this way. And that was enough playing around with my classes. I thank you guys for watching and don't forget to check out me playing with my wood. And up until next video, I wish you guys a flammable day. Ciao!